Today we're going to talk about rational functions and asymptotes. You'll find lesson 3 on page 455 in your book. Okay, a rational function is just like the name suggests, a ratio, so it is a fraction. Rational functions are fractions that have a polynomial on top and a polynomial on bottom. So it takes the form of the function of x is equal to n of x over d of x, where n of x stands for your numerator, d of x stands for your denominator. Okay? And all this is saying is that in the denominator, your denominator cannot equal 0, because like we know with any fraction, you can't have 0 in the denominator or it would not be a fraction. The degree of d of x, your denominator needs to be greater than 0, because if you had a denominator that had x to the 0, that's really just 1, which means you would have no x's in the denominator, which means you would no longer have a rational function, a function that has a polynomial in the numerator and the denominator. You would just simply have a simple polynomial function, okay? So it wouldn't be a ratio anymore of polynomial functions. Okay, so here are 3 examples of what we're talking about when we're talking about rational functions. Okay, so you can see that there's a polynomial in the numerator, x plus 2, and a polynomial in the denominator, x minus 1. Or in the second case, 1 over x squared minus 9. Or in the third case, x squared minus 4 over x plus 2. Okay. Now, as we know, because we can't have 0 in our denominator equal to 0, we have something that is called non-permissible values. NPVs is the shortened form. And the way that you calculate the NPV is you say, well, this whole denominator cannot be equal to 0. So you set that x minus 1 cannot be equal to 0. And then you just use regular algebra to solve it, so x cannot be equal to 1. Your non-permissible value for this first function is that x cannot be equal to 1. Second one, non-permissible values, well, x squared minus 9 cannot be equal to 0. So x squared cannot be equal to 9, which means x cannot be equal to positive or negative 3. And in the third one, your non-permissible value, x plus 2 cannot be equal to 0, so x cannot be equal to negative 2. Okay, so that's how you calculate those non-permissible values. That's the value that would make your denominator equal to 0. And that is an impossible situation, so it's undefined. Okay, so since rational functions are expressed as fractions, we know that the denominator cannot equal 0. We've just shown that with non-permissible values. So just grab a highlighter here, highlight that sentence, because that is very important when you're talking about rational expressions, fractions. Okay. The other thing that also is very important here is that if the denominator can be made equal to 0 for a particular value of x, then this value of this variable is called your non-permissible value. Okay, and that's what we just calculated above, and I showed you how to do that. In the examples above, the non-permissible values were positive 1, positive or negative 3, and negative 2, respectively, which is just what we calculated. Okay, so you can just draw an arrow up there. That's exactly what we did there. Okay. Now, not all rational functions have non-permissible values. For instance, here's an example of a function that has no non-permissible value. Why would that be? When you look at the value that x could be, if x was 0, we'd have 0 squared, which is 0, plus 1. So we'd have a value of 1 in the denominator. That's okay. If we had a negative number, like maybe negative 4 as our x, then if we square it, we've got 16 plus 1, we've got 17 in the denominator. So for any negative value of x, when you square it, you get a positive number, and then you're always adding one more, so your denominator will always be greater than or not equal to 0. It will always be greater than 0. If a rational function has non-permissible values, though, then the graph of that rational function isn't a continuous curve. Okay, there is some kind of discontinuity in the graph. Okay, let's highlight those sentences as well, because that's kind of the gist of our lesson today. Okay, so both sentences here. If there are non-permissible values, then we don't have a continuous curve. There's some kind of either a point of discontinuity or infinite discontinuity in the graph. Okay, and I'm going to explain to you what those things mean. Today we're going to talk about infinite discontinuity, which is the first type, and this is where we end up getting something called a vertical asymptote on the graph. But there is also point discontinuity as well, which leads to a hole in the graph. Okay, we're going to just do a couple of investigations, and then I'm going to kind of summarize this and show you what this all means. Okay, so if you just flip over the page to page 456, we have a rational function, 1 over x minus 1. And it says, since division by 0 is not defined, in other words, if this whole denominator was 0, then you would have 1 over 0, which is non-defined. Okay, so we have non-permissible values then. So if we were to calculate what our non-permissible values are, we'd have to say, well, x minus 1 cannot be equal to 0. So that means x cannot be equal to positive 1, right? Okay, so that's your non-permissible value. Now, if we were to complete the table of values below and plot these points on the grid, but we're not going to connect the points yet, okay, let's see what we would get. If we plugged in for our x, -5, we'd have 1 over -5 minus 1, which is -6. So we've got 1 over -6, which is the same thing as -1/6. Okay, if we plugged in 2 for our x, we'd have -1/3. If we plugged in 1 for our x, we'd have -1/2. If we plugged in 0 for our x, we'd have -1. If we plugged in 1 for our x, we'd have 1 minus 1, which is the case that would give us a 0 value in our denominator, which means that that is the point where this graph is not defined. If we plugged in 2 for our x, the value of our function is 1. 3, the value of our function is 1/2. 4, the value of our function is 1/3. And 5, the value of our function is 1/4. Okay, take a minute, pause the video, and plot those points, but don't join them with a line yet. Just plot them with dots. Okay, so you should have points very similar to what I have. Now, we said that the non-permissible value of x is where x equals 1. It's the line where x equals 1. Okay, so that means this line right here. Oop, I have one point that is wrong here, don't I? Sorry, this is my x equals 1. Put my points back on here. -5, -1/6, -2, and down 1/3. -1 and down 1/2. 0 and down -1. Right over here I didn't go over 2 and up 1. There we go. Over 3 and up 1/2. Over 4 and up 1/3. Okay, there we go. So this red line that I've drawn is the line that this graph is going to get closer and closer and closer and closer to without ever actually touching it. That's called your vertical asymptote. And your vertical asymptote is actually your non-permissible values. Okay, so we figured out that our non-permissible value was 1, so this is actually your vertical asymptote. If you wrote it as an equation, the equation of the vertical asymptote would be the line where x equals 1. Okay, because that's the value that would give you the non-permissible value, that's the value that would make your denominator equal to 0. Okay, so what's going to happen is this line, if we joined these dots, they're going to get closer and closer and closer and closer to that, but they will never actually touch that. So in order to investigate the behavior of the rational function near that non-permissible value, as it gets closer and closer and closer to that red line, we're going to include values of x, our independent variable, x, that are as close as we can get to the non-permissible value without actually being 1. Okay, so that's where we got these x values. They're getting closer and closer and closer to 1. And then on the other side of 1, okay, getting closer and closer and closer to 1. Okay, if we plug them in, your y value would be -2, -10, -100. Again, at 1, this equation is not defined. It would give you a 0 in the denominator. Then we have 100, 10, and 2. And if you actually pause the video now and just plot those points, or the ones of those that you can plot, we'll start the video again in a minute after you've done that. Okay, and so if you now use your best line to try to draw this, this would look like this. As it gets closer and closer and closer, but it actually never touches that vertical asymptote. Same thing with this line, it gets closer and closer and closer as it approaches that x equals 1 line, but it never actually touches. Okay? So describe what happens to the value of the function. Your value of the function, that's what happens to your y. Okay? As x gets more and more positive. Okay, so let's see, as our x values get more and more positive, so as we go as the x gets more and more positive, the value of the function gets closer and closer and closer to here, getting closer and closer and closer to 0. Okay, so the value of the function gets closer to 0. So your y, in other words, approaches 0. But again, it never quite gets there either, as your x gets closer and closer to infinity. And what happens to the value of the function, that's your y again, as the x gets more and more negative? In other words, as your x gets closer and closer and closer and closer to negative infinity, keep going this way, your y is getting closer and closer and closer to 0 again, right? You can say the exact same thing here. The value of the function, that's your y, gets closer and closer and closer to 0. Okay, once again, your y is approaching 0. Okay? So in this case, we actually have two asymptotes. We have the vertical asymptote, the red line that I drew, but we also have a horizontal asymptote, which is this x-axis that line also never quite gets to. It doesn't touch. Okay. Okay, we're going to flip over now to the next page, just to refresh our memory and highlight then the very first sentence here. that just kind of describes or explains, reviews for us what an asymptote is. A line that a curve approaches more and more closely is called an asymptote. Okay, the line never gets to it, or usually does not get to it, but it is approaching it closer and closer and closer, and it goes on indefinitely. Okay, so we can flip over now to the very last page, because the rest of these pages are just investigations to help us determine these facts for ourselves, but we're going to take their word for it, and we're going to just see how knowing about vertical and horizontal asymptotes is going to help us with graphing rational functions. Okay, so there are two, like I said a minute ago, there are two different kinds of asymptotes. The vertical asymptotes, which that was that red line that I drew. How did we determine that the equation of that line was x equals 1 in the example that we just did a minute ago? Right. That we figured out what our non-permissible value was, right? So your vertical asymptotes, those are your non-permissible values. So that we shorten that quite often. We just say those are your NPVs. Okay. Okay. So those are, the equation is x equals whatever the value is that will make your denominator 0. Okay. Your non-permissible values. Then your horizontal asymptotes, there are a couple things to understand about horizontal asymptotes. First of all, if the degree of your, what does n of x mean again? Right, your numerator. So just make yourself a note here. That's the numerator. Is less than the degree of your, the denominator. Then the line y equals 0 is a horizontal asymptote. Okay, so the easiest way to understand this is with an example. So we've got an example here of the function of x is 3 over x. Okay, so we've got the degree of our numerator. Okay, what is the degree of this polynomial in the numerator? Degree 0, right? Because x to the 0 is the same thing as 1. So this is 3 times 1, 3 times x to the 0, which gives us 3. So that's degree 0 in the top. What's the degree of the bottom? We've got an x. Right, degree 1. Okay, so what this is saying is if the degree of our numerator is less than the degree of our denominator, then the line y equals 0. Okay, so if you're picturing this on a graph, where would the line where your y value equals 0 be? Right. That is this horizontal axis, right? Okay, that's the line where y equals 0. Okay, so that would be your horizontal asymptote in any rational expression where you have your numerator has a lower degree than your denominator. Okay, another example of that would be like 2x squared over x to the 4th, for example. This one, your numerator, the degree is 2, your denominator, the degree is 4. So again, your horizontal asymptote would be this line here. That's the line that this graph would approach, get close to, but never actually meet. Okay? All right, so the next thing you need to know is that if the degree of your numerator is equal to the degree of your denominator, then your horizontal asymptote is y equals a over b. Okay, so what does that mean exactly? Here's the example. Okay, f of x equals 2x over x plus 1. Okay, the degree on top, this is degree 1. in our numerator, and we've got in the denominator degree 1 as well, right? So if you ever have a polynomial on top that has the same degree as the polynomial on the bottom, then what this is saying is the way you find out what your horizontal asymptote is you would take your A, which is 2, over your B, which is really 1x, so it's 1. So your horizontal asymptote would be 2 over 1, which actually is just 2. So the equation of the horizontal asymptote then would be y equals 2 over 1, which is just y equals 2. Okay, so on a graph, if this was your graph, that line is located right here, where y equals 2. Right, so that means that that graph would approach and get closer and closer and closer to that line, but never actually meet it. Okay. Here is another example. I'm just going to put it over in the margin where I have some room up here. You can write this down anywhere you'd like. Here's another example. If you had this equation, 3x squared plus 5 on the in the numerator, and in the denominator you had 2x squared minus 3, okay? Once again, you look at the degree that you have in the numerator, it's degree 2. And the degree that you have in the denominator, degree 2. So that your 2 degrees are the same in your numerator and denominator. So the equation of the asymptote then is going to be y equals 3 over 2. Right? So on a graph, that's the line where y is equal to 1.5, which would be about there. So y equals 3 over 2 is the equation of that line. Okay, then the last thing is if the degree in your numerator is greater than the degree of your denominator, then your graph has no horizontal asymptote. Okay? So a situation like this, where you've got x squared on the top, so degree 2, and in the bottom you've got just an x, so that's degree 1. In that case, you have no horizontal asymptote. Okay? Now, these are the 3 choices. So you will either have a horizontal asymptote of y equals 0 if your degree in your numerator is less than the degree of your denominator, or you will have a case where if you have the same degree, your degree on top is equal to the degree on the bottom, then you will have this kind of a case where it is the coefficient on top, leading coefficient over the leading coefficient in your denominator. Or you will have, if your degree on the top in your numerator is greater than the degree in your denominator, then you will have no horizontal asymptote. Okay, 3 choices. So star these 3 or draw a box around those. That's kind of the gist of what you need to know and understand from our lesson today. All right, so let's do an example then. At the bottom of the page, we have a rational function. So we have a polynomial in the numerator and a polynomial in the denominator. And the question asks us to algebraically determine the equations of the asymptotes. Okay, so first we're going to have to decide if there are both vertical and horizontal asymptotes and what the equations of those asymptotes would be. Now the very first thing you always have to do is first factor. So let's make ourselves a note. Always factor first. And there are 2 reasons for this. Okay, so you can state those non-permissible values. because you always state non-permissible values from the factored form because you can just read it right off. And so that you can see if anything cancels. Now in today's lesson, that's not important because we're not going to be seeing anything cancel in this particular example. But if anything does cancel, those are what we call points of discontinuity, which is what our lesson is on next day. Okay, so just mark that down so that when we talk about that next day, you'll go, oh, I've heard of that. That we briefly mentioned that last day. Okay, so if we were to factor this, we're going to factor our numerator and our denominator. So in the numerator, I'm looking for two numbers that will multiply to give me -6 and add to give me +1. I hope you came up with x plus 3 and x minus 2. And in your denominator, oh, we have one that's a little bit more difficult to factor because we've got 2x squared instead of just an x squared. So let's just go over maybe down here to the bottom of our page where we have a little bit more space so that we can factor this one. Okay, so I've got 2x squared minus x minus 3, and we're going to use method of decomposition. Okay, remember when we have something that's not just easy to factor with an x squared term, we've got a coefficient of x squared. Then remember we multiply the 2 and times the -3 at the end in order to find out what our two numbers have to multiply to. So 2 times -3 is -6. So I'm looking for two numbers that will multiply to give me -6, but they will add to give me -1. Once I have those two numbers, which in this case is going to be -3x and +2x, then I just plug those in, -3x plus 2x. I plug those in for my middle term, right? So -3x plus 2x still gives me this -x term. I haven't changed anything. I've just rewritten it a different way. Okay, I still have this -3 at the end. Okay, now if you remember, I'm going to factor out, I'm going to group the first two terms together and the last two terms together. I'm going to factor out any common factors that I see. I can factor out an x. So I'm going to have an x times 2x minus 3. And then I've got plus really 1 times 2x minus 3 again. I know I'm right if I have both of those factors matching each other. So then I group it. I put the numbers that are outside of brackets together, so that gives me an x plus 1 term. And I put the 2x minus 3 as my other factor. Oops, 2x minus 3 as my other term. Okay, so 2x squared minus x minus 3 factors to x plus 1 times 2x minus 3. So now I can go back up and I can put what that is here. I've got x plus 1 and a 2x minus 3 factor on the bottom. Okay, so now that I have it factored, I should be able to look right away and figure out what my non-permissible values of x are. That means if either one of these two factors, this one or this one, was equal to 0, it would be 0 times the other one, and it would give me 0 value in my denominator. So that means this one cannot be equal to 0, and this one cannot be equal to 0. Okay, so I have to set both of those. X plus 1 cannot be equal to 0, so x cannot be -1. And I have to set the other one, 2x minus 3 cannot be equal to 0, 2x cannot be equal to 3, so x cannot be equal to 3 divided by 2, which is 3/2. Okay, so I've got my two non-permissible values. Now, looking back up here, my non-permissible values are my vertical asymptotes, right? So that tells me right now I've got two vertical asymptotes. So I'm going to write vertical asymptotes. Okay, and it asked me to write them as equations. It asked us to find the equations of the asymptotes. Okay, so the vertical asymptotes, that's where x is 3/2 and where x is -1. Okay, those are the two values that will make my denominators equal to 0. So those are the vertical asymptotes. Those are the points on the graph that this graph will get very, very close to, closer and closer and closer, but never actually reach. Okay, now what about the horizontal asymptote? Well, let's look and see what the degree is of each of my numerator and my denominator. I've got degree 2 in the numerator and degree 2 in the denominator. If you look here, if the degree of your numerator is equal to the degree of your denominator, it's just this, right? And what's the coefficient of the x squared in the numerator? Right, it really is 1x squared over 2x squared, right? So my horizontal asymptote the equation of the horizontal asymptote is y equals 1/2, right? And if you need to just make yourself a note so you remember, we had 1x squared over 2x squared, and we just took this. We just took their coefficients, right? That's how we got the 1/2. Okay? All right, so for our assignment today, we're going to do questions 1, 2, and 3. And then I also would like you to do number 4 to 6 as well.